How many years do you think it'll be until quantum computing finds its way into a consumer device? Blake Johnson is a distinguished engineer and quantum engine lead. Blake, welcome to the show for the very first time. What do you think?
So I might say that in some ways it's already happened, right? Some of the early explorations with quantum were kind of fun with games, and those you can kind of make available anywhere. So I think I've seen a demo of a quantum-powered game on a phone.
Volkmar Uhlig is Vice President, AI Infrastructure Portfolio Lead. Volkmar, welcome back. Do you have a prediction here?
Quantum itself in a phone will be a big fridge. So I guess it's connected over the internet. And I can see that once there are actual applications which get a benefit out of it, they will go very fast.
And finally, last but not least, Chris Hay is Distinguished Engineer and CTO of Customer Transformation. Chris, I can usually rely on you for the wildest estimates. What do you think here?
I think it will be available on a consumer device and not available on a consumer device at the same time.
All right. All that and more on today's Mixture of Experts. I'm Tim Hwang, and welcome to Mixture of Experts. Each week, MOE helps you navigate the biggest headlines in technology with a set of brilliant minds from research, product, engineering, and more. As always, we have a slew of AI news to get through. We're going to talk about Anthropic's new model context protocol, CoreWeave filing to go IPO, and a new voice demo from a company called Sesame. But uniquely today, we're actually going to kind of like step a little bit adjacent to our usual AI topic to talk about quantum because we have Blake here on the show with us. Blake, maybe I can just have you kind of kick it off a little bit. You know, if you've been reading the headlines, you know, quantum's weird. It kind of like disappears from the headlines and then occasionally it just like comes back in force. And you just see quantum headlines like all the time. And I think one of the reasons we wanted to have you on the show is that like we're like quantum spring, like everybody's talking about it suddenly. But to my question that I opened with, it's sometimes hard to get a sense of like how close or far this technology is from becoming something like that we like practically feel the impacts of as, you know, consumer or even I guess like an enterprise. And so I guess maybe a good place to start if you want to kind of just quickly give us a capsule is, you know, cut through the hype. Like, where are we now? Like, are we very close? Is quantum nigh? Or is it like still, you know, in this kind of basic research and development sort of world?
Yeah, I mean, I think something quite interesting has happened in the past about 2 years or so, where quantum's entered really a new era, right? The first quantum computers that IBM put online were really educational tools, research tools, right? Like they're about, in some ways, about teaching quantum computing, teaching quantum mechanics, and useful to students and educators and researchers. And that was, you know, limited by the size of the computation we could execute before sort of the quantum noise overwhelmed the situation. You kind of were left with just noise. But in the last couple of years, we've now finally are at the state where we can do computations with our most powerful quantum computers that we cannot simulate with brute force classical simulation. So this is a moment that at IBM we refer to as quantum utility. And you can see that like you at least need this property for something to be useful at all, because if I get simulated with a classical computer, then I don't need a quantum one, right? So we're finally in this regime where I can do something kind of unique on the quantum device. But then we're kind of now it's the real. Now that I would say that the hunt is on to be able to put that power, connect that power to an application with that's someone really cares about and matters and has value. And so that we're kind of now in this sprint towards actually trying to take these devices and finding quantum advantage, which is that moment we can do something faster, cheaper, or better.
Yeah, and what are the kind of most promising areas for that, right? Because I guess almost it's like, it sounds like the technology is almost looking for its demo, where it's like, okay, here's a place where it's like really better than traditional computers, and you have to find a kind of quantum-shaped problem, if you will.
Sure, right. I mean, so like, I think there's things that we know about with if we had like the most powerful machines that could do kind of arbitrary sized computations. There's things that people can write down mathematical proofs that like this has better scaling behavior with a quantum algorithm than a classical algorithm. In particular, right, there's simulating nature, which is like Richard Feynman's original idea for the quantum computer came through thinking about the problems of simulating nature. And so that like has applications in chemistry, materials design, drug discovery, and so on. That becomes like a rich area. But then you also have problems, mathematical problems with structure. This is where you find things like factoring, for instance, or machine learning. And then you have kind of optimization problems where we have sort of weaker mathematical proofs about the advantage, but there's still, because of its sort of importance to business, it still deserves and gets a lot of attention. So, I mean, in terms of where we're placing our bets, I mean, I think there's a number of areas which we think are ripe for early quantum advantage. In particular, this issue of simulating nature, particularly simulating the time dynamics of a quantum system, seems like it's very possible. And chemistry is another area where the field's kind of had its ebbs and flows in terms of people being very excited and thinking and being very optimistic, and then finding pessimism again because they dug into the problem as like, oh, it's harder than we thought.
Actually, it's really difficult.
But that again had a really cool moment last year where we were, by sort of combining the power of quantum and classical computing, and it's something that IBM calls quantum-centric supercomputing, where you're sort of splitting a problem apart and having the quantum computer and the classical computer really work together. We were able to, for the first time, show really make headway on the problem of chemistry with quantum, and show like we could really finally be competitive with classical methods for a certain kinds of molecules. And now we're sort of expanding to larger molecules and trying to show again that we can kind of actually sort of reach parity with the state-of-the-art methods in the classical world. And then, of course, the hope is that, by pushing hard enough, we finally enter that territory of advantage.
Yeah, that's really exciting. So I want to make sure we bring Chris and Volkmar in, but I think one last question maybe to kind of get us there. Like, so MOE typically focuses on AI. I think because of the hype cycle, I'm in lots of conferences where people are always like quantum and AI, and like, it's right up there with like blockchain, and like kind of like all the other hype technologies are kind of like munged together in one big kind of blob. And I guess maybe a question for you is like, is there actually an overlap between AI and quantum here? Like, if so, what is it? I think a lot of our listeners kind of work in, machine learning day in, day out. I think it's been kind of voiced that quantum might have this overlap, but I think from where I'm sitting, it's like still very unclear what that would be. But I'm curious about like what people are kind of talking about in your world, and if there is actually a genuine, interesting overlap here.
I think there's two interesting directions to think about, right? You can think about using quantum to make AI better, and you can think about using AI to make quantum better. I think the two pictures look kind of different, are pretty different today, in the sense that, a lot of the early hope was about using quantum for AI. And this, I think we know, it's very interesting, but we know a lot less, right? Like, it wasn't until a couple of years ago that we could find one of these kind of formal mathematical proofs that there was something that you could definitely do better with a quantum machine, but it kind of required a contrived sort of quantum data set. And so, of course, usually where people are applying AI they're applying it to classical data. And so, that's an area where what we have available is more about heuristic methods, things which are harder to make proofs about. And yet we have definitely a different computational paradigm. So can you do something better with it? I would say the jury is still out. People are definitely trying. And we're partnering with startups and other companies that are that is their focus. In fact, you can use a sort of a quantum-powered AI tool on our quantum platform. The other direction, though, definitely that moment where we're applying AI to quantum is now, and we're really finding a lot of value in that. In particular, there's two new tools that we just released last year that are sort of directly enabled by AI. One is one of the problems you have when executing a quantum program is you start with some sort of description. In quantum computing, your program ends up taking the form of a quantum circuit. And you need to optimize that circuit so that it will run with the best performance or quality on the quantum hardware. And so we build a kind of compiler with a tool called Qiskit that does that compilation task or transpilation task to optimize your circuit. Last year, though, we upgraded that transpilation technology with AI-powered passes, using a kind of a reinforcement learning technique to automatically build optimization passes that sort of recognize patterns in circuits and find good reductions. So that was sort of one sort of novel piece that we introduced. And the other was really very much in this category of generative AI, that we used our Watson X code assistant tool and kind of fine-tuned it with quantum programming patterns based in sort of Qiskit problems and Qiskit tutorials and so on to build what we call the Qiskit code assistant. So this lives directly in your development environment and helps you sort of learn quantum programming and helps you, helps the developer write quantum programs directly in their development environment.
Well, actually, I want to bring in Volkmar and Chris here. I mean, Volkmar, maybe I'll turn to you first because it feels like we can kind of talk a little bit about that sort of quantum for AI overlap. You work with enterprises, you think a lot about AI infrastructure, like what's just like the hardware that we need to do AI. Like, I'm curious both like on two fronts. Like, I guess whether or not you have like, there are customers starting to be like, here, I keep reading about this quantum thing. Are you guys going to support that soon? And then I guess the second question is like, is that kind of like in the sort of long-term forecast for infrastructure to say, oh, well, we predict in 4 or 5 years, we really need to have these quantum computers online, or if that's not really kind of in how you guys think about the sort of like long-term planning here?
Yeah, I don't think that there is a clear path to unify the two. But on the flip side, like there are these different compute paradigms which are showing up. So I think we are going away from traditional, hey, here's an x86 box, go and hang yourself. And we are getting more into a world where the compute capacity is much more specialized for the specific tasks. And so, we have AI computers now. We will talk about this later in a show. There are whole companies which are just saying, okay, we only focus on AI capacity. I think similarly with quantum, there will be a bunch of players which have quantum computers online. The way I see this is, and this goes back to my prior life in self-driving cars, we always had the issue that when you build an AI model, you effectively need some ground truth you train it with. And we are seeing this now also coming in large language models. At the beginning of large language models was like, okay, let's just download the internet. That's my ground truth, right? And then I do next token prediction. So in self-driving, you need massive scale, observational data. So now if you think about where we are heading is, and the model is an approximation of that reality. So if you go into biology or chemistry or physical phenomena, what you need is a good sample set, which is then can be trained into a network to act as an approximation. Now, if that production of data for training a neural network becomes, decades or centuries, that's where I can see a quantum computer being extremely useful, because you can now say, let's use a quantum computer to explore the solution space because it's fast, produce a bunch of data, and then use that data to train a neural network as an approximator. And now you can actually work without the quantum computer, but you can actually look at phenomena on a desktop machine. And company before the last company, my head of data science, he came actually from CERN. CERN is doing this for decades now, that they are training neural networks, which are just physics approximations. And so this is where I think the two things can really come together.
Totally, yeah. I think this application of kind of like the AI to quantum space, Blake, you talked a little bit about, we kind of trained a code assistant, right, to be able to kind of program specifically in kind of a language that's kind of specialized for quantum. I guess, Volkmar, you're kind of raising another thing, which is pretty interesting, is like, well, in order to kind of take advantage of a bunch of these applications, we might just need to be able to generate data, and like AI is effectively like a way to get there, it seems like. So Chris, you've been uncharacteristically quiet. I'm curious if you have a view on all this in terms of kind of like future prospects for quantum. And I guess specifically, like as someone who kind of plays with models a lot, there's an interesting story here about models getting more specialized with time. But I'm curious about your take on all this.
I was really quiet because I feel really dumb in this subject when we got some super smart guys talking about quantum, and I'm like, oh my goodness, I'm just not there. But actually, I will take my super dumb approach here, which is actually, I think, to your point, you are going to need AI to be able to interact with quantum machines, because guess what AI is really good at? Explaining things like you're a 6-year-old. And I personally, I'm going to need that if I'm going to program a quantum computer, and I'm going to need to vibe code it, right? So I think that is definitely a path with code assistance, is vibe coding quantum. A probably more kind of serious one in my mind, and again, I'm just sort of thinking out there at the moment. If I think about what quantum's really good at, and again, I really don't understand quantum, but it's really all about probability, and it's all about things like error correction, and it's all about sampling. And if we think about what AI is about, it's really about probability, it's about next token prediction, and it's about sampling. So in the world that we have two very separate and different things, which are really focused on probability, sampling, and essentially prediction, I can't help think that in some way, shape, or form, these things are going to come together, whether that's AI helping quantum be able to predict better, or whether that's going to be quantum being able to help AI predict better. But I think there is a Venn diagram somewhere which bring these things together. If you ask me any further questions on this, please don't, Blake, because then I am just going to look really super dumb. But I think there's something there.
Yeah, I mean, there is definitely. I mean, Blake, do you want to respond to that? Like, there's kind of a fun take there, I think.
I think maybe you can kind of combine a little bit of what Volkmar and Chris have added here. Like, we don't see a world where quantum replaces classical computing, right? Like it's an accelerator for certain kinds of problems, and something that we see really exciting prospects for the future is about being able to the convergence of bringing different methods together. And it's kind of like you see this paradigm, this pattern already widely used in the computational science field, where people will want to study some sort of system, but the computational space is so overwhelmingly large that they don't know like where to start. And so they'll use AI models to try to identify interesting regions of parameter space and then plug in their detailed simulation model with non-AI methods. But now, in like something that's kind of an obvious upgrade to that pattern is plug in a quantum simulation model for the detailed simulation of an AI-identified interesting problem or interesting feature space. And so I think like the future really isn't like quantum or AI, it's quantum and AI.
Yeah, and I think it's particularly interesting, I think, in the context of sort of like the kind of history of computing, right? Which you started out with all these devices and then you're like, oh, we're going to converge towards a general computing device. And then kind of like, it feels like in 2025 now, we're suddenly like, well, like we're going to have special hardware just for AI. And like also quantum might be like a specific platform that we use to explore certain kinds of problems. There's kind of this like re-divergence, I guess, in some ways from like the kind of like general purpose sort of model that you'll have like kind of one sort of hardware platform that kind of will do everything.
So I think there was a paper by Google, I don't know, it was like 10, 15 years ago. And this was like an allegory to the Watson statement, the world has, needs 5 computers. And so Google said, the world needs 5 computers. And they said, there's the general purpose computer as we know it. And then they said there's search, and then we don't know what the other 3 are. And so I'm like tracking now, and I think so number 3 is probably the AI training supercomputer, which is very different structure. And then number 4 is probably quantum. So who knows what number 5 is?
Yeah, the fifth unknown.
Yeah, it's just very different compute patterns, and you're trying to find, an optimization. And the moment you can optimize something by a factor of, let's say, 1,000 or 10,000, then it's worthwhile to actually completely relook at the architecture. And I think quantum is one of these things. Like, sorry, if you can do something, in minutes, which takes 100 years, that's worthwhile actually looking at a completely different architecture.
Yeah, absolutely.
And so it's hard to say like, oh, these are not replacements because they are just so different in their design space, and then they can solve that one problem very, very well.
Well, Blake, I was producer Hans was like, you're going to have to cover all of quantum in 15 to 20 minutes. So I think we have done the best we can. Sure. I know you need to go, but before we let you go, I think one final question is, you've done a really great job, I think, kind of parsing out what's kind of important, what's not, and what's happening. On a kind of ongoing basis, I guess question for you is like, how can our audience sort of cut through all the noise in quantum news? Like, what's the important news to be paying attention to? What should people be reading? Just if you have any final parting recommendations on that front.
I would caution our listeners that like there is a narrative out there that quantum computers can't do anything until we have error correction. And certainly like the most general purpose algorithms we know of are large computations, and we need systems that can execute really large circuits. But like we're already in this realm where we can execute circuits that we can't simulate. I think it's actually harder to believe that nature doesn't permit anything useful to be done between now and something which is a billion times larger. And so, like, I think the thing to pay attention to is the kind of steady march of progress of the performance of the machines, as people sort of build up the kind of the fundamental ingredients to just do larger and larger computations. Because what we can do with these machines is going to be directly connected to the scale computation that we can reliably execute.
Yeah, that's great to keep in mind. Well, Blake, thanks for joining us, spending some time this morning, and hopefully we'll get you back on a future episode because I'm very sure that there's going to be more quantum news this year. Well, that was great. I'm going to move us on to our next topic. So the thing that was dominating all of my group chats and my machine learning AI social media this week was the Model Context Protocol released by Anthropic, or the MCP for short. The way Anthropic describes it, I'm just going to quote from their website, is, quote, MCP, right, provides a universal open standard for connecting AI systems with data sources. And people have just been frothing at the mouth on how excited they are about MCP. Chris, let me turn it over to you. When I read something like universal open standard for connecting AI systems with data sources, are they just talking about APIs? Like, why is MCP important? And I'm curious about what you think about the release.
Okay, so MCP's been around for a little bit of time. So what's actually made it super cool, though, is that it's actually hooked up into some of the editors like Cursor or Klein, which is my particular favorite in this case. So you can then go and access MCP from on there. What is cool about MCP, underneath the hood, it is just JSON RPC, so remote procedure calls under the hood there, right? So there's nothing wonderful, but what they have done is absolutely standardize it. And they standardize it in probably three ways, which is important. Number one is that you can expose your resources. So resources is going to be things like, maybe it's a database schema, maybe it's your GitHub schema, and then you can go and look at an individual file. And then the second one, which is probably the most important one, is tool calling. So I can say, these are the tools that I've got available, these are the parameters that you need, and then I can go and execute those tools. Why is that important? Because traditionally, we've been using a thing called function calling. And the thing about function calling is you need the functions to be on your machine locally. But with MCP, I can have these servers serve up the tools that are available, and they can be hosted in different locations, they could be remote, and therefore I can start to mix and match and do cool things. So coming back into the Cursor example, there might be a tool server that has got sequence diagrams, mermaid diagrams, or bar charts, and therefore I can say, hey, I've coded up something, and then I'm going to say, hey, go and generate me an architectural diagram for this. Or maybe there's a compiler, go compile this. Or maybe there's an MCP server for AWS, and then I will just say, go deploy this piece of code that I built and put it on the server there. So actually, this ability to access tools in a federated fashion, and everybody's building marketplaces around this, really starts to supercharge the models and the VS coding environments, because I'm no longer just restricted to working with my code, but now I've got access to my tools and ecosystems, and I can mix and match and do them together. And more importantly, the model and the agent is orchestrating and in control of that, which makes it super, super cool.
Were we always going to end up here? I know there's kind of a very hyped dream of agents, I don't know, 12, 18 months ago, which is eventually the agents just get good enough that they can kind of just like do this integration without having any special standard. But I guess maybe, I don't know, maybe that was always kind of a pipe dream, right? Like that we would always have to rely on some standardization to allow these agents to effectively use these tools versus the agent just gets smart enough and kind of the problem gets solved out of the box.
Yeah, we were always going to end up here. And I think there's a few shifts in the technology that has got us there. So number one is MCP is a good one. But actually before that, we really needed function calling. We needed a standardized way for models to be able to know how to interact with APIs. And you also needed a thing called structured output. So one of the things that models have been really bad at in the past is if you ask a model to say, go generate me this piece of text, then it can just go and generate it in whatever format that it needs, which is fine. But the problem is that if I'm dealing with an API and there's maybe a schema behind this, I don't want it sort of hallucinating the schema that it comes out. It needs to be exact to be able to make that interaction. And then the last one that's really important is the context length, right? So the working short-term memory that the models have. If they're too small, you're not going to be able to do a lot with agents in the first place because it's working with tiny paragraphs of information, right? Whereas now the models are all sort of 128K by standard, 256K for some of the newer models, in the millions for some of the Google models as well. So actually the working memory the models have are huge. So they understand standards, how to do function call. And now we've standardized this at an API level in the same way that REST was standardized for sort of microservices, etc. So this now opens this up into the tool marketplace. And then, as I was saying the other week, then the next logical step is going to be that we're going to have the agent marketplaces, and then we're going to have agents multi-collaborating with each other. So this step of MCP and tool marketplaces is really the first step, but there's more to come.
Volkmar, question for you is like, if you think Anthropic has the juice, right? Like this is kind of a battle of standards. They're throwing out their standard and it's already very popular. It's integrated into a bunch of editors. But it's like by no means certain that the model producer, the model creator is the one that defines the standard. Like I could imagine a world where I guess like the databases are the ones that say, okay, well, if you want to talk with our kind of protocol, this is the standard that you're going to use. I guess kind of question for you is kind of in this competitive landscape, if like you think Anthropic's got the edge, like this will eventually be the kind of base standard for everybody.
I don't think that this is. I think we should ask the question differently. So I think Anthropic is hitting a point where the value of their model is higher if they can interface with an ecosystem, right? And because they cannot build every application under the sun or house every application under the sun. And so what they are doing is they're opening up their access to information, which is potentially locked away, and make their own model, more useful. And so someone has to drive the standard. And OpenAI right now hasn't been, stepping up to the task, so it's coming from somewhere else. That's how I see it. Now, if you look at OpenAI did like almost a year and a half ago, they just said, point us at the Swagger API and we just integrate with it, right? And that was their answer. And so I think we are getting to a point where it's an indicator that models will actually be much more autonomous, not constantly human supervised. If you look at the traditional initial models, like the interface language to the model is English. And now suddenly we're saying, well, not really. It's remote procedure calls to computers. So it's now computers talking to computers. And there's already like, what is the model? If two models want to talk to each other, should they communicate through English, or should they have some gibberish they could talk to, right? So there is, we are now just enabling software to be directly invoked from the model. And so making the models effectively access the rest of the world. We are already accessing search. So that's deeply integrated. So, models go out and do research and they go to search engines. But search engines are still kind of written for humans. So the queries you are sending are kind of natural. But I think this is just the next logical step. Also, you need to standardize to actually do quality assurance. And so if you don't have a standard, how do you say my model is actually doing the right thing? And so if you don't have those standards, it just becomes very, very hard to do that. Because as Chris said, like the model just gives you some tokens back and sometimes they are misformed. And so you want to actually have a unit test which says, no, it's actually correct syntax. And so those things all happen through standardization. And then suddenly, things can talk to each other. So it's a natural progression. I'm surprised it hasn't happened before.
That's right. It's actually like maybe actually delayed a little bit. Well, great. I'm going to move us on to our next topic. One of the big news stories of the week, at least for me, was CoreWeave, which was, if you haven't been watching kind of the AI hardware, AI cloud space, CoreWeave is kind of like one of the most exciting kind of, I would say, like upstarts in the space. They originally started, I think, as a sort of crypto infrastructure company, so building sort of specialized clouds for crypto mining. I think they noticed that AI was going to be a big market, and they've kind of like gone fully in on AI. And they've benefited, I think, from the fact that they have a very close relationship with NVIDIA and have had kind of early access to a lot of the kind of like next generation chips as they've been coming out. And as a result, CoreWeave has grown hugely, and it is now filing to go IPO. And I guess, Volkmar, maybe I'll turn it to you. I think you're the obvious person to kind of respond initially to this is, I'm interested in how you think about the market for sort of like companies that specialize in AI compute. Because, I almost kind of thinking about it, I'm like, well, there's these like 10,000-pound gorillas in the space that really dominate the cloud market. It's interesting to believe that like, hey, a company that just kind of specializes in this one area can like survive and become its own gigantic company, right? But I guess I'm curious about like what you think the prospects are for sort of these more specialized kind of compute companies, and I guess specialized compute in AI in particular.
So this goes back to the thing we talked about like 10 minutes ago.
There's 5 computers.
5 computers. Yeah. And I think there is a wave of new companies coming out which are entering the cloud space to serve that specific niche of supercomputers. So if you look at what CoreWeave is doing, they are not only giving you AI capacity, but they very specifically give you an AI training cluster. And so when you are going to CoreWeave, you are not buying 10,000 H100s, you're buying 10,000 H100s wired up into a single supercomputer, and they are running that single supercomputer for you. And so the IBM, for example, we announced it a while back. We are having a relationship with CoreWeave, and so we are running training jobs in CoreWeave, and it's simply it's a very natural progression in these compute demands to say, I don't want to have the asset on the books, or I don't want to build the in-house capability to operate these very, very large machines. And so there's an economy of scale similar to the cloud, how to operate this and get really good at it. And I think CoreWeave is probably one of the leading companies. They are really, really good at their job. And so I think it's a natural progression. But on the flip side, it's a new market will evolve of these, high performance computing hosting companies. So now the big question is, can the traditional ones like in Azure, Google, and AWS, how are they doing in this world? And it seems so far CoreWeave has an edge here because they are saying we don't worry about virtual private cloud networks internally, et cetera. We are just giving you a computer, and it just has a lot of GPUs in it.
It's still a little counterintuitive to me. It's kind of like, like you think about like the deep amount of like capital that like an Azure has access to. Like it kind of feels like they would be like, sure, we can just offer that too. We just have like way more money to do that than these kind of smaller providers can. So it almost kind of feels like, I don't know, Chris, if you've got an opinion on this, or Volkmar, if you do, like, it seems like this additional edge they have is that there's something about deploying these clusters which is kind of so sort of unique, I guess, in terms of know-how, that it's actually pretty difficult for these like kind of maybe traditional players to kind of like easily just kind of shove these other companies out of the space. Is that the right way of reading what's going on?
If you look at traditional cloud vendors, they are vendoring out thousands of individual computers. So they are not, their DNA is not clusters of making 1,000 machines work in concert, but their approach is, I have 1,000 machines and they all kind of limp along, and once in a while one fails and I give you another one. And if you look at training workloads, that's not sufficient. So you have you need 1,000 machines which actually stay up. And so any fault or any network congestion also has quite dramatic impact. So, NVIDIA had a lot of challenges with HBM. So if one of these GPUs has an HBM issue and there were silent high bandwidth memory errors and corruptions, your training job will just, either fail or not make forward progress or forget what it just learned. And so one of the things CoreWeave is doing is they are monitoring literally every wire in their cluster. So the connectivity from the CPU to the PCIe switch, from the PCIe switch down to the card, all the links, et cetera. They deal with link flapping, et cetera. So to keep that one computer up. And the traditional approach in the cloud is like, just take it offline and give you a different one. And so there's a different DNA you need to have as an operator to actually operate these machines. And this is pervasive in your control plane and your monitoring infrastructure, et cetera, because in the cloud, typically you just take one machine offline and nothing happens.
Chris, you want to jump in with your hot take?
If I think about I think I've said this before, but if I think about the Bitcoin, everybody started on, CPU, then they moved to GPU, then they moved to FPGAs, and then they moved to ASICs, etc. For inference, we're seeing the exact same thing. Everybody's building their own inference chips, etc. So what does that leave it down to? It leaves it down to training compute, right? I.e., I'm going to train models. And what's the very thing at the moment we were literally discussing last week on the podcast, which is the era of pre-trained dead, right? So actually, we've moved into kind of reasoning models. We're going to take a base pre-train. So there's going to only be a few companies that are doing massive trains at that point, perhaps, and then everybody's going to be into this sort of inference time commute. So where is the market? There's a big market at the moment, but does that market stay there? And then you've got to look at what's going on in the desktop market. So if we look yesterday, Apple with their new M4 Studios, where you're going to be able to take something like the DeepSeek R1 model and be able to run that on your desktop. And then we discussed on the podcast a few months ago the NVIDIA boxes where you're going to be able to train. So I think that the fine-tuning market, is that going to stay on the cloud, or is that going to be devices that people have, or is it going to be anywhere else? And then if I think of the cloud providers, back to your point, do you think AWS and Azure is going to let somebody else eat their lunch? They're going to be like, no, we are going to put that capability in ourselves and we're going to squish you.
Yeah, I mean, that shift basically to reasoning models, it's interesting to believe that it basically favors the incumbents, because I guess an inference world looks a little bit less like the training world. Like that effectively, like almost the meta moves back to, wow, it's broken, just pull it out, put a new one in. You don't think about that? Yeah.
No, the post-training is now much more than the pre-training and post-training, but simply because it's a mix of training and inferencing. And so I think that and the complexity for that post-training phase is sometimes now 5 to 10x more expensive to the post-training. Now, on post-training, you still have your model, your training live in a cluster. But what you're doing is you need to, your loss function just went from a couple of milliseconds to a couple of minutes. So that's the actual challenge here. And so there is a bigger balance between, how much you have in your training cluster versus how much infrastructure you need to have live to do your loss function calculation. Now, the loss function calculation there still needs the weights of what you just trained. So these are very, very large training clusters, which now have more of a mixed workload because the computational cost has shifted, but the fundamental problem that you need a big HPC machine hasn't. And so, I mean, from my perspective, big question is the market big enough that Google, Amazon, and Microsoft are saying this is so critical to us because otherwise the workloads move to these esoteric vendors and then they will have a drag that we don't want to allow this. And then there are effectively two options for them: buy or build, right? And if you look, like you go across Google, Amazon, and Microsoft, and their heads of the training clusters are all ex-HPC guys. So they have the talent in-house. So now it's a question, how fast are they moving? And then, do they see this as a market which is big enough? If you look at CoreWeave, it's a couple of billions. If you look at Microsoft, it's a couple of trillions. So there are 3 orders of magnitude, of market cap. So it may just not be so critical right now, or now that those companies are coming online, they will go and have to do it themselves. So I think we will see. I think, Chris, you're right. The chances that $1 trillion businesses take out $1 billion businesses is extremely high, and the negotiation power is better. We'll see, but I think fundamentally what we are seeing is that there's a different compute paradigm which allowed that market to exist, and it was underserved. And because it was underserved, this company exists. So now let's see if they close the gap.
I agree with that. It is definitely an underserved market. But as I said, every single one of these companies, whether you're an AI provider or a cloud provider, are investing in designing and building their own chips to bring down the costs, right? And Volkmar, I totally agree with you, which is latency on inference is key. But actually, that's the biggest focus at the moment, is getting the inference chips right. So actually, to my point, is having big, massive clusters. And yes, it does take a lot of data, and it is big training runs and big clusters to do these kind of post-tune phases. But the reality is it's a different mix of workload, right? In that sense, and therefore there's new techniques, and where those guys are really just saying, here's my big cluster, kind of go for it. So I just can't help thinking that anyone who is an AI model provider is really going to be investing in that space themselves with their own chips, their own infrastructure. And I get your buy versus build point of view, but as you say, kind of small numbers at the moment, and I just don't see the big cloud providers being prepared to hand over so much cash to a kind of third party in that sense.
We could go on at length on this, and I actually do want to return to this point because I think it's very interesting about like how like the landscape of infrastructure is going to look with all of these pressures. And I think this kind of third path where the really big companies are basically like, what's a few $1 billion? And they kind of leave the market alone. It is kind of it's definitely a path that I never thought of before, though we shall see. Well, great. Well, I think for the last segment, because we only have a minute, just wanted to quickly touch on a news story that popped up. We'll mention it just, I think, because it was sort of, again, widely chattered about online. There's a startup called Sesame, which was launched by one of the Oculus co-founders that's been working on sort of synthetic voice. And they released a demo that I think, at least personally for me, has kind of like gone over like what they argue to be kind of like the uncanny valley of like voice interfaces. Like, you know, to be totally clear, right? Like, I don't really use voice on OpenAI. I don't really use voice on Anthropic. But this is like the first time where I was demo. I was like, okay, yeah, this is like almost getting smooth enough to the point where it does sort of feel like interacting with a human. Maybe we can just kind of do a quick round the horn on just like, you know, if Chris, Volkmar, you guys have played around with it. You know, do you think it's worth for people to check out, or is it overhyped? Do you think we're finally there from a voice standpoint? Just kind of quick takes before we close out the episode.
Oh my goodness, that model got me in trouble with my wife. I put that model on at about 11 o'clock at night just to interact with it. And my wife's like, who are you speaking to? Well, it's like, I hear a woman's voice. And I was like, oh my goodness. And I had to switch that thing off, right? Because it was so realistic. And I was just like, oh my goodness, I can't talk to this anymore. So that model is incredible. Actually, they have solved a few things. They've solved the latency problem. They've solved the kind of utterance problem, kind of just, you know, the silence, the waiting, and the model will come back. It is truly like a natural interaction, and you feel it. You feel as if you're talking to somebody else at the other end. So I think this is going to change everything. You know, I did a thing about contact centers, about latency, etc. You know, you don't think that we're going to see those types of models powering customer service experiences in the future? Absolutely. This is coming down that road, and they're going to kick off agents to do workflows. The model is incredible. And I think if anybody who has interacted with any other voice model before and like, it's not quite there yet, or, oh, that's terrible, go check out this model, because actually what they've done there is incredible.
All right, Volkmar, parting shots. Hyped, overhyped?
I agree with Chris. It's amazing. I tried it in the office, so my wife was not listening to it. No, I think it's very interesting because it shows the other end of the spectrum. Right, so we have these kind of military-style Siri conversations, you know, which command you around where to drive, and this was really smooth, like chatty, you know, friendly, funny, and so I think there is now we have two ends of the spectrum, and I think now we can populate all the other points, and so now you can make these models, you know, for pretty much any human interaction. So I can't wait that, you know, when I call into, you know, any airline, it doesn't tell me that I need to wait for, like, I had one of the airlines telling me it's 2 hours and 40 minutes until the next agent can talk to me, and they can just pick up the phone and talk to me. So I think this is a great extension to the spectrum here. And, you know, it's also good that someone is nice to you and when you're driving the wrong way.
Yeah, also critical.
It might be too sassy for the airline scenario. You know, you call up, go, my flight is delayed. You go, but did you actually get there on time, Volkmar? Did you,
Exactly.
did you plan enough? Did you, and so maybe it might be a little bit too chatty for that scenario.
I think it's a really good way to see, where we can go. It's like, if you can do that, you can do anything. It's really a different emotional state they manage to capture. And so I think the real interesting part is, how do they express that? How could they make a model where they could get those types of emotions into the model and express it mathematically? And I think if you get that dial, then that dial is the powerful part.
I agree with you, actually. That is probably, that word emotional is the most important one, because that was my real point when I interacted with the model. It was like, oh my goodness, this feels real. There was that. It was really weird. It was just that feeling that you had, and no other voice model has been able to do that. So I think this is something different. They're very open about the techniques, and in fact, I think it's getting kind of open-weighted pretty soon as well. So I think this is just a game changer.
Well, you heard it here first. You should check out the Sesame demo. And that's all the time we have for today. Chris, Volkmar, thanks for joining us as always. We'll have to do the duo show again at some point. And thanks to all you listeners for tuning into Mixture of Experts. If you like what you heard, you can get us on Apple Podcasts, Spotify, and podcast platforms everywhere. And we will see you next week here on MOE.